Hi, this video is about some everyday examples of inertia. The more massive an object is, the more inertia it has. And that means the more the object resists change. More mass means harder to change its motion. So as an example, everyday example, let's say you were just really craving some Chick-fil-A and you show up at the door and you realize it's Sunday, of course. But you're already there and you want to get in, you want to get some Chick-fil-A. And so the only option you have is to break down the door. So how do you break down a door? Well, if you try angry fists against the door, you're not likely to succeed. And that's because an angry fist moving really fast, even if it's moving really fast, it doesn't have a lot of mass. Your fist relatively is pretty small. It doesn't have a lot of inertia. And so whenever it collides with the door, it's pretty easy to stop your hand. Well, okay, you might be thinking, what if you try to body slam? Okay, better, right? You get more of your body, not just your fist, but you get your whole body moving. And that's a lot more inertia. So you slam your body against the door and you might get it to budge a little bit, but it's probably, if it's a good door, it's probably not going to break down because you threw your body into it. It's a better option because you got more inertia. It's harder to stop your body than it is your fist, right? But the real option is, of course, to get a battering ram. Chop down a tree, large tree. It's got to be a big tree, big trunk, okay? Hoist up the tree trunk and get it moving at a good steady speed. I'd say at least 20 miles an hour. If you can get it faster, even better. Because once you get a giant tree trunk moving at a high speed, because it's so big, it's got a lot of mass, it's got a lot of inertia, and guess what? It's really, really hard to stop a giant tree trunk coming at you. A little puny door is just going to fall right over when it comes face to face with a giant, massive tree trunk. And that's because that tree trunk has got a lot of inertia. The battering ram just rolls right down the door and finally you get some fries. So for this reason, in physics, mass is often defined in a way that's a little unusual. You've probably heard before that mass is defined as the total amount of matter in an object. And that's true. But in physics, we have a slightly different definition for for mass. In physics, mass is actually a measure of the amount of inertia that an object has. So if you have a 200-gram bowl of Cinnamon Toast Crunch, it's got more inertia than a 100-gram bowl of Cinnamon Toast Crunch. More inertia means it's harder to change its motion, harder to move it around. So mass is a measure of how much inertia an object possesses. Now, it's still true that mass is defined as the total amount of matter in an object, but these two definitions are really the same thing. But in physics, we often say mass is a measure of how much inertia an object has. Here's an example. So I've got two seemingly identical cans of Diet Pepsi here, okay? And they look identical, they're the same size. Are they the same mass? Well, how would we know that? Well, of course, we could measure it on a scale, right? But in physics, we know that mass is not necessarily tied to like how much is being pulled down. That's actually weight, and that's a little bit different. So in physics, we can test how much mass something has by testing how much inertia it has. So to do that, I want to see how resistant these cans are to moving. If it's really resistant to moving, it's probably got a lot of mass. So I'm going to give each can a flick. Just the same flick. I'm going to try to do the exact same amount of flick power, okay? So I'll flick the first can. Here we go. Okay, it moved a little bit. It clearly has a lot of mass in it because that was a pretty hard flick and my finger hurts a little bit now. Let me flick the second can with the same amount of force. Okay, saved it. That can was empty. It had no mass inside of it. And we know that, you know that, without even looking inside the can, you know that because mass is a measure of how much inertia something has. If it moves really easily, obviously, it doesn't have a lot of mass. So, let me show you an example of a kind of tricky problem that you might see related to this idea. Okay, so, for example, you might see a problem like this where it says to rank the vehicles in order of their inertia. It's a trick question, so don't fall for it, okay? We've got 3 cars right here. You can see their masses and their speeds. First car, mass 1,000, speed 30 miles per hour. Second car, mass is 1,000, speed is double, 60 miles per hour. Third car, truck, the mass is 2,000 kilograms, speed is 0, it's not moving at all. So which one of these has the greatest inertia? It's kind of a trick question because you don't really need to know the speed. All you need to know is the mass. Because remember, mass is really a measurement of how much inertia it has. So if you're looking at this, let me grab my pen. The mass of the first 2 cars is the same, 1,000 kilograms, 1,000 kilograms. So these 2 masses are equal. That means they have the same inertia. And how does that inertia compare to the truck? Well, these are 1,000 kilograms. This is 2,000. So this is twice as much mass, which means this is twice as much inertia. This truck has more inertia than the cars. Now you might think that's wrong because it's not even moving, but that's the trick, right? It doesn't have to be moving. The movement speed does not matter for how much inertia it has. If it was moving, let's say I changed the speed to 60 miles per hour for the truck. Okay, now it's moving the same speed over here. It has not changed its inertia. It is moving fast now, but it's just as difficult to change its motion as it was when it was moving. It wasn't moving at all. It's still difficult to change its motion because it's massive. It's really difficult to shake it up. So that's all I have for you in this video. Remember, how you do anything is how you do everything.